First, I want to thank, of course, the organizing committee for giving me the chance to talk here. And I want to tell you a bit about chirality at the nanoscale, and specifically in semiconductor nanoparticles. So a few basic concepts to begin with. So chirality is a geometric property of any object which is non-superimposable with its mirror image. And of course, it is a key aspect in biological sciences and chemistry, but also it turns out that in more fundamental fields of physics, and for instance, a lot of physicists are interested now in how the parity violating properties of the weak force might be the generating force of chirality at macro scale. So physicists also take interest in chirality. And we use the term chiroptical activity to describe the unique interactions of light or electromagnetic radiation with chiral objects. And one of the most common effects we study is circular dichroism. There are two images of chiral objects, the very famous image of our hands, which are chiral, of course, but in the context of this talk, also an image of quartz crystals. One of the phases of quartz is actually chiral. So it's a chiral crystal, and there are the two mirror images here. So circular dichroism is the differential absorption of left and right circularly polarized light by any chiral object, defined as written here. And more often we use the quantity of dissymmetry, which is a normalized quantity. Basically, it's the circular dichroism divided by the absorption. And the reason for that is that when we compare different samples, a lot of times we don't know the concentration at different samples, and circular dichroism is dependent of concentration, while dissymmetry is not dependent of concentration. And this is a typical, at the bottom is a typical circular dichroism spectra of different conformers of proteins. And there are two features to look at a typical spectrum. One is the magnitude of the effect, and the second one is the polarity of the sign. It's either below or above 0, standing for stronger absorption of the left or the right circularly polarized light. And so the first measurements of this type of effects in inorganic nanoparticles was done by Assaf and Wetten. They've synthesized very small gold nanoparticles which are capped with chiral molecules. And they were able to measure circular dichroism response at wavelength, which we know that correspond to electronic transitions of the metal and not the chiral molecules that cap it. This was followed by many works, and more recently, there was a demonstration in a semiconductor quantum dots by Gunko and co-workers in cadmium sulfide quantum dots. And again, the observation is always CD responses at wavelength, which we know that have to correspond to electronic transitions of the inorganic core, and not the molecules capping it. And there are three mechanisms which are proposed and discussed. The first, as you can see on the left image, is that basically the whole core is chiral. Somehow the chiral molecule forces the whole nanoparticle to become chiral. And this was based on some theoretical work which is considered not so reliable by now, and probably this mechanism never really takes place. The second mechanism described in the middle image is that only surface atoms are slightly distorted, and this is enough to generate a CD response in the inorganic core. And the third mechanism on the right is that nothing is basically chiral in the structure of the inorganic core, and the effect is just an electronic effect, some sort of an interaction between the chiral molecule and the inorganic core. For instance, and this was proposed by Govorov, some sort of a dipolar interaction between the chiral molecule and the dipole response of the nanoparticle, which might be a plasmon response or an exciton response, depending on the material. So in some of our past work, we tried to tackle the mechanism by studying the size dependence of the phenomena, which is always informative in different effects, but also the material dependence. So we've measured the strength of of chirality, basically chiroptical activity in different samples of cadmium sulfide and cadmium selenide quantum dots, later on also zinc selenide. And what we've seen is that there is a very strong size and material dependence, which was a little bit counterintuitive to what was previously discussed. I can tell you that we have discussed the different mechanisms in light of these results, but this is not the subject of this talk. What we've also seen is that CD is surprisingly quite a powerful tool to characterize electronic level spectrum of quantum dots. And you can see in the bottom images, the left image is the absorption spectra of cadmium sulfide samples, 7 different samples of growing sizes. The middle image is the corresponding CD spectra, and the CD corresponds very well to the absorption, and CD redshifts, much like any other phenomena in quantum dots, which is quantum confinement-related phenomena. And the most important image maybe is the right image depicting the strength of chiroptical activity as function of some measurement of size. In this case, it's a function of surface to volume ratio. And you can see that, at least for cadmium sulfide, which is the black dot, chiroptical activity decays very strongly with size, maybe exponentially, but this is the experimental results. And you can see, well, the blue dots are cadmium selenide, and the pink dots are zinc selenide, and you can see that there is a very strong material dependence. So cadmium sulfide exhibits much stronger chiroptical activity than, for instance, cadmium selenide. But anyway, induction by a molecule on a non-chiral core is always a weak effect. And we are trying to generate much stronger effects. And of course, this is interesting because you can take the very special properties of nanoparticles, combine them with chirality, and then you get a new form of response where you can control the optical response of nanoparticles by simply changing the polarization of the light interacting with them. So this is interesting. And we are looking for ways to achieve much stronger effects. And perhaps the most intuitive way is to work with chiral crystals, and that is materials which truly crystallize in chiral space groups. And we went back to the ideas of Pasteur, which did the fundamental works in this field at 1848, where he could crystallize crystals of some organic molecules and crystals of their salts, and separate these crystals. And he was working with macroscopic crystals, so of course he could just take them with a tweezer and separate the two enantiomers. What is done afterwards was to resolubilize them and do chiroptical spectroscopy. So he discovered chiroptical phenomena this way. And there's an image in the bottom of, these are actually the models that he designed, where he sculptured both mirror images of chiral crystals. And to this date, there wasn't any attempt to try the same at nanoscale and combine chiral properties with nanoscale properties of nanoparticles. So we tried to tackle this problem, and we chose to work with mercury sulfide, and its chiral phase, which is called cinnabar. This is a very unique material which has been studied quite a lot in bulk. It crystallizes in a chiral space group. I mean, it's either one of the two enantiomorphic space groups. And the structure is basically helices of mercury and sulfur atoms which spiral around the c-axis of an hexagonal unit cell, as you can see in the bottom image. And this is an interesting material because, first of all, it is the most chiral mineral existing. And second, it has a band gap which allows us to conduct CD spectroscopy because it absorbs visible light. So it's convenient for us. So the idea was very much inspired by what biologists and organic chemists know very well, that if you take a chemical reaction in the presence of some chiral molecule which perturbs it, you can direct the growth of, you can direct the outcome of the reaction to one image with a lot of excess. So we try to do the same. And the chemistry we've developed is based on nucleating nanocrystals in the presence of very strongly binding chiral molecules. And in this way, we hope to direct the growth of crystals to one mirror image of the nanocrystals. And we have succeeded. We get opposite enantiomers of nanocrystals by using opposite enantiomers of the perturbing molecule, the perturbing chiral molecule. These are images of the nanocrystals we got. This is mercury sulfide. There is a small scheme of a helix which represents the direction of the helixes of atoms relative to the c-axis of each nanocrystal. These are the measurements we've done. So the left top image is the absorption spectrum. So it absorbs throughout the visible spectrum. On the right at the top is the CD response. And you can see that there is a CD signal. And it's opposite for both enantiomers of the molecules. So we are able to get both mirror images of the nanocrystals. And the important parameter at the bottom left image is the dissymmetry. And now the peak dissymmetry for these crystals is already of the order of 10 to the minus 2. While at all other previous works, it's around 10 to the minus 4, 10 to the minus 5. So we've improved maybe 2 or 3 orders of magnitude. And this is already several percentage of the light incoming. So this is actually might be applicative for some purposes in chiral nanomaterials. And you can see I've added the point of mercury sulfide in green to the image you've seen before. And you can see that it's way off scale with all other materials in terms of dissymmetry. There's also very interesting dependence of morphology. So we can get nanocrystals which are much more deformed in shape. And while the absorption spectrum does not change very strongly, well, it slightly changes, but not very strongly. And this is because we're also not working in the regime of very strong confinement. So the absorption spectrum does not change very much, while the CD spectrum at the bottom changes dramatically. And we still don't really understand this completely, but you can see that CD spectroscopy is very sensitive to the morphology and crystallinity of chiral nanocrystals. And I would like to just conclude and state some future directions. So we know that size and material dependence of induced chiroptical effects are a good way to resolve the mechanism. And the group of Daniel Neuhauser at UCLA is helping us by doing the theory for these effects. But these are weak effects. So controlling chiral crystallization and separation is a much more promising way to obtain strong chiroptical activity. And there are a lot of materials that exist to continue this work. I mean, for instance, tellurium, the element tellurium crystallizes in a chiral space group. But it is also metallic, basically. So you can think of metallic nanocrystals, which are chiral. This is supposed to be very promising for metamaterials, or at least there is some prediction on that. And if you want to get some properties, for instance, in the IR regime, you can work with silver selenide, which is also chiral. So there are a lot of different materials to study. One more project we are working on, which I find very interesting, is that because these nanocrystals are actually highly non-linear material, we are trying now to conduct non-linear chiroptical spectroscopy. And we are measuring the second harmonic generation circular dichroism response of these nanocrystals. And what we think is that we can get the response from a single nanocrystal. So we are now developing basically the way to do single particle chiroptical spectroscopy, which is, I think, pretty much impossible to do now. And one other thing we're doing, we are also exploring in these crystals the effects of Rayleigh and Raman chiroptical activity, which are pretty elusive effects, which are very difficult to study in molecules, but are in many ways easier to study in chiral nanocrystals. So we also have some results on that. So I would like to thank Gil, of course, and the members, other members of my group, our collaborators, the group of Dan Oron at Weizmann Institute, Sasha Govorov at Ohio University, which does the theory in these systems, and also Daniel Neuhauser, which helps us with the theory, and to the Nano Center, of course, for the fellowship, and thank you for your attention.